welcome back from the lunch session, and I'm very glad to be the chair of the third session of our online conference today. And my name is Dirk Müller. I'm the head of the Institute for Energy Efficient Buildings and Indoor Climate. And in this session, we will focus on buildings, especially we will focus on renovation roadmaps for the building stock. So it's not a single building, it's more how we actually proceed with our whole building stock. And this is a very important part for the energy transition, but also a very difficult part because many different parties are involved. We have two internal presentations, one from our institute and one from the Institute for Future Consumer Needs. And also I'm very happy that we have one external guest from Switzerland, who will also share his view on building portfolios. Starting with the first presentation given by Nico Fuchs, and he will show how to deal with challenges in building modernization based on some calculations and optimizations. I look forward to your presentation.
Thank you, Dirk, for the warm words of welcome today. I'm also looking forward to this session because we see some interesting topics, and I'm happy to give my contribution in the field of optimization models for the building modernization. Because if we imagine that the majorities of the building that we use today will still be in use in 20, 30 years, I think it's clear that we need to modernize the majority of them to achieve net zero. But let us first look where we are today and where we need to go, because if we consider national transition studies, they give us a number of how many heat pumps a year we will need to install to achieve our climate targets. And they speak about around 1,500,000 heat pumps in this decade and even over 900,000 in the next decade if we want to achieve net zero in 2045 in Germany. If we compare now the sales of heat pump in the last years, then it's clear that the numbers fall short from our targets more than factor 2, even in the best year we had in 2023 for the heat pump market, and the same as well as for the renovation rates for the building shell. Here the national studies talk about around 1.5% or even more required renovation rate, and we have nearly the half at the moment. So it's clear that the modernization rates still fall short of the targets. But why is that? We have different challenges to face in building retrofitting. Let me classify them into 4 categories. The first one are technical challenges. If you look back, the energy systems in buildings were quite simple. Maybe we had a gas or oil boiler just to supply the whole energy demand, and that's basically it. And nowadays, we want to integrate heat pumps, we want to integrate PVs, couple it with energy storage. So the orchestration of all those components in a heterogeneous building sector is quite challenging. And for sure, anyone has to pay for it. So we have economic considerations, and here we have to face high investments with long payback periods in the building sector, and face uncertain energy prices, uncertain subsidies, which is quite hindering investments in building modernization. And the regulatory framework here is still unclear at some points at the framework conditions. For example, if you think of Tennessee law, of different regulations in the electricity sector coupling. So still unclear. There are still some challenges interacting with organizational challenges, because here we need acceptance for the retrofit measures at the market for the tenants who also need to pay for it. We need to coordinate all of those modernization measures. And now this quite complex modernization decision, we can help by modeling tools to just allow a structured comparison of this complex modernization decision with all of those interactions. And therefore, research already uses modernization tools, optimization tools, because we saw one of them at the beginning of my presentation. There we saw some numbers for the heat pump implementation, so there are already existing studies. So why do we need our work now? Let us maybe check which existing transformation studies do at the moment. So normally they start by a building typification. They divide the building stock into representative archetypes, and then they normally employ some static calculations for energy demands for those archetypes, employ constant seasonal efficiencies, like for example, constant SEOP of a heat pump converted to final energies, and then use again constant yearly factors to calculate for yearly emissions and energy costs. If they now apply different scenarios, for example, assume different penetration rates for heat pumps, for building insulation, they have a scenario ranking for costs and emissions, and now they can choose those scenarios that achieve climate targets, for example, in the lowest possible way of costs. This is what they do nowadays. This is quite strong if you want to have a fast, scalable approach where you also can integrate other consumption sectors like the electricity sector, but it falls short in covering the interaction between the insulation decisions and the HVAC system behavior. Let me explain this, because in the building modernization decision, everything is a little bit interconnected, because if you insulate your building, you lower your demand, you also can lower your supply temperatures in the building, which increases your efficiency of the heat pump. So the SCOP of the heat pump will depend on the building where you install it, and therefore those existing studies fall short in covering those interactions. What do we suggest instead? At our chair, we use a design optimization approach where we can implement multiple varying parameters for user behavior, economic and technical parameters. And now we calculate our energy demands not on a yearly balance base, but on an hourly base in a higher timely resolution, which allows us to have some dynamic behavior for our building envelope, for our thermal demands, and to also model operational performances with dynamic efficiencies on an hourly base, taking into account all of those interactions that are building specific. Here we integrate different boundaries, for example, like subsidies and regulatory minimum requirements that we can just consider their influence on the market. We can also evaluate the availability of resources, because resources as budget or labor force is limited on a national scale. So we can also use those models to allocate them. And for sure, we can also think about some local requirements as source availability for different types of heat pump. We formulate all of this into mathematical optimization models. We can solve them for the objective functions regarding cost or emission, and derive optimized modernization strategies for our insulation and as well for our technology, covering heating devices, covering solar devices, etc. As I think use cases examples, they make the modeling more clear. I will present the models in the following at 2 use cases. The first one will be the national building stock of Germany, where the challenge is to allocate limited labor to different building types. And the second one will be a local distribution grid, where we can guide the electrification of building energy systems by such planning models, taking into account issues like grid overloading, like peak capacities of buildings. Let me start with the first example of the national building stock. With a little background, in different studies, we see that we already have a shortage of skilled workers, of labor in the market already now. And it is to be expected that we will need over 100,000 additional skilled workers if we want to succeed with the energy transition. just until 2030. Now we ask us the question, does this influence the way we modernize our buildings? So we have just limited labor. We have some modernization measures that we think about, different building types in the market. And now we think about how to allocate this labor capacity to different buildings to decide about the modernization measures as well as the time period that we want to modernize our buildings here. And like the national energy system studies, in this example, we divide the building stock into archetypes. And in the following, I will apply a free optimization where we see first the best way to modernize the building without taking labor into consideration. And then second, I will add some labor constraints to the model that we can see how the allocation of labor influences the way that we modernize the buildings. Let us jump directly in some results. Here we can see different years of the roadmap, therefore the installed capacity of heating systems and PV. And here we assume for this illustrative example that we only have gas-fired existing heating systems. And now we can see that the model decides to install air-to-water heat pumps here in green in the majority of buildings, backed up with electrical heaters and combined with PV units, and that the gas boilers are phased out in the first 10 years of the roadmap. And this is the suggested way of the model to achieve climate neutrality at lowest possible ways. Yeah, also under consideration that the electricity grid is also decarbonized in these projections. And if we consider the insulation decisions, we can see them on the lower diagram for the components, windows, for the walls, for the floor and the roof. We see that for the average U value, which is depicted here, that the average U value directly drops at the beginning of the modernization roadmaps because our model decides that it's beneficial to insulate the older buildings directly at the beginning, because then you benefit a lot from the energy savings over the whole roadmap. Now you might ask, is this possible to modernize nearly half of the buildings just at the first time step? I would also agree that it's not, and therefore let us consider the case of limited labor capacity in the following. And here, let us define this scenario as reference, as 100% labor capacity, all we would need, and just shorten the capacity of labor that we have in the market. So I did it here for 3 scenarios. 100%, the reference scenario we already saw, 70 and 50%. And what we see here for the costs in red and emissions in gray, that both KPIs increase significantly. And here the emissions nearly are 3 times higher with only half of the labor capacity than they've been with the free labor capacity. And why is that? If we now check again our installed capacity, this is the same diagram as before for 100%. But if we now compare it to the limited resource case, we see that we still have some gas boilers in the late years of the roadmap, and even more if labor is shortened even more as well. This is combined with steadily rising average U values. I cannot show them here, but here you have to trust me. And why is that? I mean, it's clear if you just have fewer labor, you need to take the decisions that are faster in the implementation if you want to cover your energy demands of the building. So the model here goes for more gas boilers than heat pumps, because it's just not possible to install all of the heat pumps in this scenario. So far, I would say as we would have expected, but the interesting thing of our model now is we can check the allocation to different building types. So now we can evaluate building archetype-wise which modernization measures are chosen, and I want to show it here because of the lack of time in an aggregated way. So we see it here on the left diagram. We see how the emissions are allocated for each building type. So the share of emissions of all single-family, multi-family houses, office building, and other buildings. And on the right, we see the share per building age, where I clustered them into 3 age groups here. And if we compare the 100% scenario with the 70% scenario, we see one interesting thing. So the red bar here nearly doubles in its height, meaning that single-family houses contribute to a larger share of emissions, because if you just have limited labor, do allocate them, do prioritize your larger buildings where you have a higher impact with just only the installation of one heat pump, for example. Do also prioritize older multifamily houses, because here you have a higher impact of your modernization, which is quite interesting, because they are, if we consider the landlord-tenant behavior, the most difficult buildings to modernize nowadays. If we now compare the last scenario, the 50% scenario, we see a similar share to the full capacity. And this is just because in this scenario, the model can just decide to only renovate the building stock. So it just does what is necessary to keep the energy systems running. There is no capacity for modernization, and therefore the distribution is more or less like the initial one. Let us take a short break here and summarize what we've seen in the first example. We've seen that limited labor capacity has driven the portfolio toward higher heat demands, greater fossil dependency, elevated cost and emission, and that those labor capacities, they do shift the modernization focus towards larger and older buildings. And now we could employ those models for sure to other use cases, do more detailed planning building-wise, would be possible in future works. I want to use the remaining time for a second example. This one is just a little bit smaller, and this is the case of a local distribution grid. Because, as we already heard today, the electrification imposes risks on our distribution grids at every level, and also on the low voltage distribution grids. And here we have to face the risk of overloading the electrical grid capacities if we do not reinforce them. I think we all would agree that there will be some need for grid reinforcement, but we would also agree that we cannot reinforce all the grids at once in a certain year. So here we ask ourselves, in local distribution grids that cannot be renovated within the nearest future, does the capacity of those grids affect our cost and emission optimized modernization strategies? So this is the question we want to face here. And for the use case, I brought a typical low voltage grid, the IEEE European Low Voltage Test Feeder, representing a typical low voltage distribution network. It connects 55 connection points, and here I assumed them all to be single family houses of the 60s. So it's the example of a rural district with old single family houses. And we assumed just a small transformer capacity of 2 kilowatt ampere per connection point, which is also on the lower rate just for rural grids. So it's just a small transformer that we consider here, but more or less the typical example of a rural single family house district. Again, let us see the results of the optimization. In the first case, we employed just the cost optimization without any emission targets, just to check what would be the most cost efficient under current energy price forecasts. We see again installed power and average U values on the both diagrams. And here we see that PVs, first of all, are cost efficient in most of the buildings with suitable roof areas. We can also see that gas is still important in this portfolio, because it's just still cheap, even with the forecasted gas prices to employ to use gas boilers in older buildings. But we can also see that small heat pumps in some buildings combined with PV can be cost efficient. And here we see some modernizations in the buildings. What I didn't mention so far, why do we have 2 bars for each year? And the left case is free grid capacity, and the right one is constrained grid capacity. And here we don't see any difference. So meaning that here our grid constraints do not impact the modernization strategies, because I mean, it's also clear we still have some gas, we do some modernizations, so no problem for the grid in this case. But let us consider a more interesting scenario, a trade-off between cost and emissions. So we do want to lower emissions, but in a cost-effective way. And let us concentrate on the left path first. We see that the gas boilers are phased out within the first 10 to 15 years of the roadmap, and we have larger shares of the blue line here of heat pumps. At the beginning, it's not reasonable to put all of the gas boilers directly away, because the models phase them out step by step when the emission factor of the grid decreases. And we still use PV in some buildings. But now, if we compare the left and the right chart, maybe here, we see that there is a significant higher amount of gas in the buildings than in the case with free grid capacities. So meaning that in this case, the grid capacities necessitate to have some share of gas boilers, to maybe have hybrid heat pumps. In this solution is a transitional technology until here we modernize the building shell, and then this has the same effect. It also decreases your peak loads. Let me show you the last scenario, the emission optimal way, where we have more modernization here. We lower our U values, where we phase out gas boilers quite early in the next 5 years maybe, and change everything to air source heat pump. And this is a quite interesting effect. If you tell electricity grid to be net zero in the future, then the buildings would say, yeah, okay, let's do direct electrical heating. I mean, that this cannot be the case, we would all agree, but in this emission optimal scenario, it would be the best solution. So what have we seen here? We have seen that limited grid capacity necessitates either the grid reinforcement or improved building insulation, or maybe that we use some hybrid heat pumps as a transitional technology in the future. And please allow me to summarize my findings and my presentation on the last slide. What have we seen today? We've seen that current building stock models, that they are strong in demonstrating national trends and considering dependencies across energy sectors, but fall short in modeling interactions between the building envelope and technology. I presented optimization models that consider building technology interactions and detailed building modernization planning, which can help us to align in the future regulations in a targeted manner with regard to cost-effective emission reductions. What I haven't shown you is the evaluation of who bears the costs for this energy transition now, but I'm happy that I do not have to do this because we will see more in the next presentation. Here are my resources I used in the presentation. Thank you for your attention.
Yeah, Nico Fuchs, thank you very much for your contribution. And as in the last session, we will have questions at the end of the 3 presentations. So we can directly move to the next presentation. And the next presentation will be done by Karl Seeger, and he is a researcher at the Institute for Future Consumer Needs. And he will especially look at the impact on regulations on the building stock. And as you already could learn from the first presentation, this is quite important to adjust regulation also to technical needs we have in the energy transition. So I very much look forward to your presentation.
Okay. Thank you for the kind introduction. And first of all, I have to say, maybe my title is a bit misleading. My presentation focused more on the short-term regulatory measures and their impact on energy poverty. In the end of my presentation, I will give a brief outlook on how to model the heating transition and the related regulatory measures and their impact on energy poverty. And I think maybe that's an interesting linkage between our model, and that was our microsimulation model that was developed of our share, and maybe a promising combination or linkage to the model Nico Fuchs just presented. Okay, let's start. So in the last month, we have seen that in the media, the focus, when it was about affordability, was almost all the time about affordability and competitiveness of the industry. And it's true that it's for the energy policy in Germany a key objective to maintain the industrial base in Germany. And we have already seen that first measures were taken. For example, we have seen the tax or electricity tax reduction for the German industry. But, and that's important, but we haven't seen comparable tax reductions for the households in Germany. So it was promised in the coalition agreement to reduce the electricity tax for the households, but until now that does not or didn't happen. But the affordability or households affordability is also key or super important, because without household affordability, parts of household could and actually already do oppose to the energy transition and the heating transition. So yes, in my presentation, I would like to present the results and assess how the transition or how some regulatory measures affect the affordability of households. And first of all, I want to highlight it's complex to model the interplay of the energy transition, their related regulatory measures on the affordability. Therefore, we need, or it requires, a careful analysis. And for my presentation, if I speak about household affordability, I mean energy poverty. So in the beginning, I want to give a brief overview about the term energy poverty. Okay. There are a lot of papers about the definition and measurement of energy poverty. And in total, well, actually it's a common approach to define energy poverty thresholds. If a household is below or above this threshold, that depends on the threshold, he is classified as energy poor. So in total, we differ between 2 or 3 different types of energy poverty thresholds. We have the technological energy poverty threshold. That would be something like the effectiveness of the building installation. Then we have something like the energy consumption specific energy thresholds. That's, for example, the energy use per square meter. And then that is for us the most important one, the economic energy poverty thresholds, which again divided in subcategories. We have the absolute and we have the relative economic poverty threshold. And the most famous one is the so-called 10% indicator introduced by Brenda Boardman, which is an individual relative economic energy poverty threshold. And it says that a household is energy poor if they spend more than 10% of their income on energy bills. Okay, and for the further analysis, I want to use a multidimensional relative economic energy poverty threshold, the so-called low income, high cost indicator. It states then if the equivalized household income is below 60% of the median equivalized income, and this household spent more than 10% of their income on energy bills, this household is classified as energy poor. Okay, then next step, I want to look at the regulatory measures, and following Heller et al. 2024, I want to classify these measures in 4 categories. So we have the short-term measures and the long-term measures, and we have regulatory measures with a low impact and a high impact on energy poverty. We start with the upper left. Here we see the quick fix. They have a short term, but only a low impact on energy poverty. That could be something like a lump sum transfer from the government to all households. Then we have the so-called temporary solution. That would be something like subsidies from the government to low-income households. This has a high impact because this temporary solution directly addresses low-income households, but it's not a good long-term solution because it reduces the price incentives and therefore discourages energy efficiency improvements, of example, for buildings. Then we have the lasting solution that's not focus of today's presentation. Could be something like websites on energy efficient behavior. And last but not least, that's the linkage to what Nico Fuchs presented before. We have the structural change measures. That could be something like energy efficiency standards for buildings. And these standards or these measures would have a high impact and a long-term effect on energy poverty. Okay, but as I mentioned in the beginning, for today's presentation, I want to focus on the short-term regulatory measures and their impact on energy poverty and inequality. Okay, for the analysis, we used for our paper a so-called microsimulation model. In this microsimulation model, we combined different household samples for Germany, for example, the Einkommens- und Verbrauchsstichprobe from the Forschungsdatenzentrum and the pretty famous ZÖP data from the DIW in Berlin. And we combined all that, added forecasts and assumption about energy tariffs and data about energy consumption. And then that's the most crucial or most important point. We added household-specific price and income elasticities of energy demands to the data sets as they were estimated by Priesmann and Practicno 2024. With all this, we are able to simulate households' consumption changes in response to price changes and income changes. Then we can consider exogenous changes like changes in energy tariffs, changes in subsidies, and so on to assess the impact of price increases of different regulatory schemes on distributive justice, on energy poverty, and on ecological sustainability. Okay. Yes, we applied the methodology from the last slide. So we applied the microsimulation to the short-term relief measures, or to actually assess the impact of the short-term relief measures during the energy price crisis 2022-2023. And we published the results in a working paper. So if you're more interested in the results, please read the working paper or check the working paper. And first of all, we need more data. So we need some data about the energy carrier prices for the respective years. Here on the left side, we can see the prices for electricity, for heating, which is in this case gas, and for mobility, which is a combination for diesel and petrol for the respective years. And as I mentioned before, we need a bunch of different elasticities. With the elasticities, we can add heterogeneity to our model. For example, we can see that the poorest households react way more aggressively to changes in energy prices. For example, the poorest households would reduce their demand for heating by 0.65% in response to a 1% increase in gas prices, while the richest household would only decrease their demand by approximately 0.1% in response to a 1% increase in gas prices. Yes. Okay, so with this elasticity data, we can just simulate heterogeneity and insert that in our model. Then for our paper, we focused on 5 different relief measures. We have the energy allowance, which is just the lump sum transfer of 300 euros to all tax liable employees. Then we have the child bonus, where every family or every person receiving Kindergeld was given 100 euro per child. Then we have the famous Tankrabatt, which was a temporary reduction, tax reduction for petrol and diesel from June to August 2022. Then we have the gas price cap, which limited the gas price to 12 cents per kilowatt hour for up to 80% of the 2021 consumption. Everything above this threshold was priced at market price. And then last but not least, we have the so-called housing benefit reform, Wohngeld Plus, which expanded the income limits and added a heat cost component. Okay, for our study, we defined 4 different scenarios. So we have kind of a baseline or start scenario where we use the 2021 prices, where we do not allow for policy measures. I mean, there are no price increases, so there are no policy measures necessary. And we do not allow for behavioral adjustments. So all elasticities I have shown before are set to 0 in this case. Then the second scenario is the price shock only scenario. Here we consider the price increases in the crisis, but still do not allow for policy measures or behavioral adjustments. Then we have price shock plus policy. We have the price increases, allow the government to intervene with the regulatory measures like the Gaspreisbremse, but still have elasticities set to 0. And then the last scenario is the full simulation, where we have the price increase, where we allow for regulatory measures, and where we allow the households to adjust to the increase in energy prices. Okay, then the results. I think the color is a bit different, but I think it's not a problem. In blue, you can see the result for the baseline, red for the price shock only. Gray, in this case, I think it's actually green, is price shock plus policy, and the full simulation results in yellow. Up there, you can see the average electricity and gas consumption on the right side per household for the defined scenarios. And we can see that in the price shock and the price shock plus policy scenario, the consumption is increasing compared to the baseline scenario. And that has nothing to do with the energy price crisis. It's more a model intrinsic assumption, because we assume that from year to year, households replace, for example, their oil heaters by gas heaters or by heat pumps. So we have a model intrinsic mechanism here that leads to this increase. But more interesting is the full simulation scenario, where we can see that in both cases, the households react to this price increase by decreasing their electricity and gas consumption drastically compared to the baseline case. Okay, then let's focus finally on the energy priority. We can see that in the baseline case, which is kind of the pre-crisis situation, approximately 7.6% of our households were energy poor, according to the low income, high cost indicator. And we see that considering only the price increase, we have a sharp increase in the share of energy poor households by almost or more than 2 percentage points. And then considering the regulatory measures, we see they have or do not have a huge impact, because they can only dampen the increase moderately. But we see that the household's behavior is key to reduce the number of energy poor households, because here we can see that the increase is dampened by more than 50% compared to the price shock only scenario. Okay, then we can look at the inequality, and for our paper we use the Gini coefficient as an indicator for inequality. And Gini coefficient of 0 would mean total equality, while the Gini coefficient of 100 implies total inequality. We can see a similar pattern for the Gini coefficient as for the energy poverty, we see an increase in the inequality for the price shock scenario. Considering the regulatory measures, we see that the increase is dampened, and considering the behavior of the households, we see only a small increase in inequality. Okay, that's right now more aggregated data. The microsimulation gives us also the possibility to look deeper into the income distribution. On the next slide, we can see the result for specific regulatory measures on the income decile. So we can see on the left side with the bars here that in absolute terms, the poorest households benefited less compared to the richer households, while in relative terms, we have in reverse U shape, meaning that the middle income households benefited the most in relation to, or in relative to their household income. Okay, we have a different picture for the gas price cap. So actually in absolute terms, it's the same. Richer household benefited more in absolute terms, but we have the opposite case for the relative terms, meaning that the gas price cap was more effective in addressing the energy poor households. Okay, I think, yeah. The microsimulation gives us also the opportunity to look deeper into the emissions by income decile. And we can see from here that, for example, the poorest households produced the largest emission reductions compared to the baseline case. And it makes sense that the emission reductions are the highest for the full simulation, because in this case, we allow for behavioral adjustments facing the energy price increases. Okay. Maybe for the end, and I skip some slides, we can also aggregate the data of the results of the microsimulation to have some results on a national level. So on the upper left side, we can see the total energy consumption for all households combined in our microsimulation. And we can see that, as it makes sense, for the full simulation, we see a sharp decline, while there's only a minor decline for the price shock and price shock plus policy scenario. For example, we can also highlight the total policy measure cost, as you can see on the left side there, where we can see that whenever we consider behavioral adjustments, it becomes cheaper for the government subsidies because there's less consumption to subsidize. Okay. We have more slides, but yeah. Okay. Then maybe I'll go to the last slide, and that's a connection to what Nico did before. Right now, I focused only on the short-term regulatory measures, but in the near future, I would like to expand the microsimulation. I would like to add investment costs to the model, and also focus on something like income-based subsidies for the CAPEX, and would also interesting to integrate a tenant or owner logic into the model. I mean, there's already something integrated, or there's already the CO2-Kostenaufteilungsgesetz integrated, but would be interesting to look much deeper into this topic. And if I integrate all the CAPEX, it would be possible to assess the impact of regulatory measures like the Bundesförderung für effiziente Gebäude or the Gebäudeenergiegesetz. So I think by integrating that, we have also good linkage to what Nico is doing. And by doing that, we could answer research questions like which regulations are most effective in increasing the renovation rate without increasing energy poverty, or does the mandatory replacement of fossil fuel boilers lead to unreasonable cost burdens for tenants in certain regions? Yeah, I think that's it.
Yeah, Mr. Seeger, first of all, thank you very much for your presentation, and also this presentation will be open for questions. Please use our Q&A or use our chat function, and after the next presentation, we will be able to answer all the questions. But first, I would like to go to the third presentation, and I'm very proud that we got an external speaker involved, and this is Georgios Mavromatidies, and he actually started his career at the University of Thessaloniki, and then he spent 6 months at Imperial College in London. Later on, he switched to ETH Zurich, and he spent more than 12 years at this university. So a lot of his background on this topic actually comes from this time of his research. And now he works for EMPA in Switzerland, and he is the head of the Urban Energy System Lab. So I'm very happy to have you here, and I very much look forward to your presentation.
Great, thank you very much for the introduction. I hope you can hear me, by the way.
Perfect.
And when it comes to video, I'm okay to having my camera off, but if I try to turn it on, it says that it's been disabled by the host. So it's okay to go either way. Provide heating and electricity into the building, but also how do we combine that with retrofitting, so from the demand side. What element of the building to retrofit, what material to use it, also considering the embodied emissions that it comes with it, and also the depth of the retrofit. Do we go for the minimum prescribed by the code, or do we go for a deeper retrofit? And at its core, Mango Red makes two key decisions: what to do and when to do it, for both for the demand and the supply side, but also it tries to capture the timing. So what measures should happen now and which can wait. The model finds strategies that minimize total costs and CO2 emissions, including both operational and embodied ones. And it works on a long-term multi-stage planning approach that is aligned with asset managers thinking. What we also did in the model, but we do not optimize for it, is try to calculate the rents that the building will have after its retrofitting intervention, using legally mandated formulas and building value calculations for reporting on constraints. And technically speaking, the model is then formulated as a mixed integer linear programming model, which means it can represent also discrete retrofit choices. Now, if we look at one example building in Zurich, this is a figure that demonstrates the output of Mango Red, namely the trade-off between total cost and CO2 emissions. And on the x-axis, we move from low emission strategies on the left to low cost strategies on the right. And the top chart shows the total cost breakdown by components, while the bottom one shows the emission split between operational and CO2 emissions. And as we can expect, of course, reducing emissions can quickly drive up costs, mostly because of higher capex for insulation, renewables, and so on. But interestingly, across all strategies, the embodied emissions are those that dominate. So which tell us that if we only decarbonize operations, we might be missing an important element there, which is the material and construction impacts, and which start to matter more and more. And if we look at, for example, a specific building, the model allows us to deep dive even more in the strategies that we have. So on the left here, we have a timeline of investments when different measures are implemented across the horizon. So we have a mix of envelope retrofits early on, and then some renewable supply technologies like PV and heat pumps a bit later in the timeline. And then on the right-hand side, we have the embodied emissions associated with each measure. So technologies like PV, while crucial for decarbonization, also bring a non-negligible embodied footprint, which needs to be accounted for if we want to really have net zero strategies. So overall, Mango Red helps us understand where the emissions come from, what drives the costs, and how timing shapes both. And now let's take a step back and move from the individual building level to the portfolio level, because large-scale investors don't manage one building, they manage hundreds or thousands across, in some cases, different regions or even countries. So here's the basic idea. On the left, you see where we basically left off, the building level trade-off between cost and CO2. And then for each building, we can generate a set of these solutions, some cheaper, some cleaner, and for example, by having some preference in terms of a CO2 emission budget, select one point. Now, when we go to the portfolio level and we have multiple of these Pareto fronts from our model, it's not as easy then to do this exercise one by one. So what we did there is instead developed a new optimization model that uses the output of Mango Red as parametric input and seeks to choose one strategy per building while minimizing the total portfolio cost and also considering CO2 constraints and other net zero goals. And then a question that we had to deal with as in the first step was how to create the necessary policy conditions to facilitate portfolio decarbonization. Namely, how should emission limits actually be defined? Should they apply to every single building or the portfolio as a whole? So on the case of the building level CO2 limits, we have a limit that is applied to each building in the portfolio, meaning that each building must meet a defined CO2 target. And this is more the approach that we also see today in building norms and building regulations. For example, by defining a specific CO2 per square meter target for the buildings, and then choosing the option that is the cheapest for each building. Of course, then that means that we might have buildings like the one on the right that are much harder or more expensive to decarbonize, and they might be left out. And the question is, of course, what do we do with these stranded assets? On the other hand, if we apply a portfolio level CO2 limit, not just in every building at a time, but as a whole, we can have more flexibility because the model can invest more heavily in deep retrofits for cost-effective buildings, while letting more complex or heritage protected buildings, for example, decarbonize later. So this is an example shown here, where the chosen solution for each building moves towards deeper emissions, allowing the stranded asset on the right to also survive in the portfolio with a bit of a higher emission impact. So the overall portfolio still meets the CO2 goal, but in a much more cost-efficient way. So we evaluated this approach and both policy designs using data from 3 portfolios of Swiss large-scale investors, together covering more than 600 buildings and a combined asset value of multiple billion euros. So on the left side, we see the comparison between the 2 policy approaches. And then it's clear that portfolio level policies lead to more attractive outcomes, achieving the same CO2 reductions at lower overall cost than building by building limits. And because these portfolio strategies also integrate long-term plans from Mango Red and the detailed building level strategies, we can also show the full decarbonization pathways, how emissions evolve over time, and how also the investment breakdown happens. So what technologies do we need to invest in the portfolio? What measures need to be implemented for each building at a time? So this approach already gives us a structured way to plan large-scale portfolio decarbonization, but of course, the job is not done yet. So there are still some important limitations in our approach that we needed to address if we want to make this be truly usable for both investors and also policy design. So it's powerful, but we had some blind spots. First, because of using optimization at the building level, we might overlook some diversity. So we get optimal solutions, but in practice, there is no perfect plan. We might have combinations of measures that perform almost as well, but offer flexibility for implementation. But given that we use optimization, these measures are largely overlooked. And then second, we used a total cost minimization approach for the portfolio, which might not necessarily capture how investments happen at the portfolio level, because LSIs are also interested in investment pacing over time or smoothing capex to align also with budgets. So if we do not have these two elements there, even technically optimal plans might not be financially feasible for investors in the real world. So in the current study that we have a working paper on, we try to extend our framework in two key directions. First, at the building level, we are exploring near optimal solutions, not just one best retrofit plan, but a set of solutions that are almost as good, to maybe have more flexibility if, for instance, certain materials or contractors, as also Nico was saying, aren't available at the same time. And then at the portfolio level, we try to not only focus on minimizing the total cost, but introducing some more time-balanced investment planning to design decarbonization pathways that are cost-effective and realistic over time. So essentially what we try to do is bridge a bit optimization with practicality in this case. So some methodological elements here at the building level, where we try to focus on near optimal solutions, meaning solutions that perform almost as well, but differ in terms of structure and timing. So to do that, we explore two variants. One is the enforced retrofit, which, as the name implies, at least one type of envelope retrofit must occur in a specific investment stage in our horizon. But we still allow some flexibility to the model to also implement other measures in other investment stages. And then we have the even more restrictive approach of the exclusive retrofit, where all envelope retrofits are restricted to one defined investment stage and are not allowed to happen outside of that. And the reason we focused on envelope retrofits is because they are the most costly ones, the ones that need the longest planning, and the ones that basically drove the model results the most. So this approach allowed us then to lock in different timing assumptions and restrict the model a bit more to create a more diverse solution space for portfolio optimization later. So at the portfolio level now, as I said, the task was more to have flexibility towards investment pacing. And a reminder, our main task is we get all these Pareto fronts from the building level, and we have to choose one solution for each building. So in the first approach that we had before, which I call now the naive approach, we only looked at the total portfolio cost and some CO2 constraints, and that was basically it. Of course, we have more constraints to choose one solution per time, per building, but this I don't show here for simplicity. And then we have two more objectives, where we have basically the risk-averse approach, which limits the maximum cost in any given investment stage for the investor, and the balanced minimum cost difference approach, where we minimize the difference between the highest and the lowest investment stages, giving more smoother and realistic investment trajectories. Now, a couple of examples. Here we illustrate what happens with near optimal solutions for two example buildings, one multifamily house with a gas boiler and one industrial building with an oil heater. And you can see that these are the classic Pareto fronts that come with pure optimality. But by adding these constraints, like forcing the envelope retrofits in a specific investment stage, for instance, we slightly move away from the optimal curve and get still valuable and practical alternatives. And these alternatives then can help us achieve better coordination across the portfolio. And of course, on the right-hand side, the exclusive approach being more restrictive means that it introduces, of course, a bigger penalty in terms of both costs and emissions to our solutions. Now, if we look at what happens in this red box area in more detail, we see that basically these near optimal solutions are achieved by postponing some envelope retrofits, for example, by delaying facade or window upgrades to a later investment stage. This doesn't change the overall costs dramatically. You can see we move, for example, a couple of tons of CO2 up, but instead what we gain is temporal flexibility. So instead of having to retrofit everything at once, we can spread investments more evenly, which at the portfolio level might mean smoother capex curves. And this is exactly what we saw at the portfolio level, where we simply saw that if we minimize only the total costs, we have very high investment peaks in certain stages, as shown on the right-hand side here. But when we introduce alternative objectives, like the min-max and the min-difference approach, we start to spread investments more evenly over time without losing too much in terms of total costs or emissions. So these formulations give us more flexible, more flexible and implementable pathways with minimal cost penalties while still meeting the same emission targets. And here we see that even more closely with a few selected points, where in the early stage strategies like points 1 and 2 from the minimum total stage cost, we have very high peaks in the first stage, which also reflects nicely the results that Nico showed earlier. But the more balanced strategies like points 3 to 5 spread retrofits across stages, reducing peak investment needs and allowing for more manageable decarbonization planning. So to wrap up, I'll take a step back from the methods and look at what this means for us a bit more broadly. So first, large-scale investors play a critical role in the building transition. They own significant shares of the building stock, and their choices largely define the speed at which decarbonization happens. And progress really depends on coordination across scales, so it is important to align building-level retrofits with portfolio-level planning, budgets, and long-term goals. And our approach provides a structured framework to explore what, when, and how to retrofit in both levels, aligned with real investment decision processes. Of course, at this stage, I have to acknowledge all the colleagues that are behind this work. This was truly a collaborative effort between ETH Zurich and EMPA, with each person bringing, of course, unique expertise and from modeling to empirical insights, behavioral dimensions as well. And as a final closing, I've shown you so far mostly the research elements that we developed as part of our project and ongoing work. But of course, the real impact also happens when such methods move beyond the lab. And this is exactly where Optimo comes in, an ETH Zurich spin-off that builds directly on this research. Their software, what they call real estate decision intelligence, helps asset managers and investors plan decarbonization pathways for entire portfolios. It uses the exact same methods that we saw today, optimization of what, when, and how to retrofit, but wrapped in a user-friendly platform that works with minimal data and across building types, and is now being scaled and rolled out in multiple countries in Europe and beyond. So that's an example of how scientific models can evolve into tools also that drive real investment decisions, turning optimization from research theory into actionable low-carbon strategies. And with that, I'd like to thank you all for your attention.
Yeah, first of all, thank you very much for your presentation. We're running a little bit short on time, but still, I think we have some questions from the chat. And maybe first question actually goes also to the first presentation to Nico Fuchs. And there has been a question, okay, now we see in 2024, there are less heat pumps installed than we thought. So does it have any impact on future results regarding your calculations, or how do you proceed with this kind of finding?
Maybe allow me the question back. So the question would be, if we do not achieve the installation rates for heat pumps, what then? If we don't succeed with this? Yeah, please. Mm-hmm.
Less than 23. So was that statistic from last year and wasn't all in it yet? Or
okay, this was just the example of the motivation. Now I get it. Thank you for the explanation. This was just market rates, sales of heat pumps, just statistics in the last year. So in 2024, the market rates dropped. So we model at the models what should be done to achieve targets. And then I would agree, if we don't achieve to increase the heat pump sales to the level that we calculate, it would not be possible to reach net zero. So this would be too low. And therefore, yeah, we need to
fasten our modernization at all levels. And I think then the approaches taking into account real investment behavior, like we've seen in Georg's presentation, they are really crucial because we need to convince building owners.
And maybe to add, is like not a statistical effect, was a real market effect based on rising pricing and for heat pumps, and also based on very unclear policy situations. And this actually had a big impact, and so everyone was selling heat pumps was of course very unhappy about this development. And then second question goes to the second presentation, and then we have the definition of poor that can be very different. Actually, using different definitions has an impact on your findings and results, or it's all more or less equal?
No, I think there's a huge difference depending on what kind of definition for energy poor you use. And I mean, I think no definition of energy poverty is perfect, so they have all shortcomings, but there's kind of a trade-off between using more complex definitions for energy poverty, but then it's harder to explain that to the public, or it's just harder to explain. Maybe they are, yeah, so there's no perfect definition for energy poverty.
Thank you very much. And then last question goes to Georgios. First of all, thank you very much spending your vacation with us today.
It's been a pleasure.
Pleasure to have you here from Scotland, and hopefully in perfect weather conditions. And one question from my side, you showed for companies owning a big portfolio of buildings, it's quite difficult to say what is the most important thing for them. And for them, I mean, it's a mixture of rent today, estimation on future rents, and also how much money you can ask for a building in the next years, depending on the amount, for example, of free flats you can expect. How do you make such a complicated assumption for the future or for the estimation of the value in your software?
Yeah, so, well, I mean, in all honesty, we are trying our best, and we are trying to base our assumptions in as reputable resources as possible, typically align with public scenarios, so federal scenarios in our case, that show trajectory of prices, of market rates for various aspects. But of course, can I guarantee that these are correct? No. I would even argue that they're most likely going to be wrong. What we do allow, however, in our approach and our models is for our targeted audience to play with these assumptions, have some scenario approaches. And what matters is, of course, that they will implement and do the first step. Of course, these approaches have to be rerun periodically. It's not that one develops a 30-year portfolio plan and forgets about it. And a more academic approach would be, of course, to consider uncertainty considerations, so Monte Carlo simulations and even stochastic programming and methods like this. But with the computational complexity that these models already have, going towards the stochastic domain becomes quite a bit of a challenge. So we are exploring now also meta-model based approaches and other methods like that to potentially even enable robust and long-term decision making at the portfolio level.
Okay, thank you very much for your answer, and enjoy your time in Scotland. And
thank you so much.
We now have a very short break of 5 minutes, so we will start again at 2:30 with the last session of our online conference. Thank you very much.